The modern battlefield is now saturated with high-power RF noise, specifically designed to drown out the L1, L2, and E1 satellite bands. Right now, tiny 450-gram drones are flying through these blackout zones, remaining stable where traditional systems drift and fail. Portable jammers pushing just 10 to 40 watts of power are capable of creating GNSS blackout zones that span for miles. When a drone dependent on satellite navigation enters these regions, it loses the timing and Doppler inputs required for route following. Without that external link, the platform loses positional confidence and triggers a fail-safe descent. For an armored vehicle crew, this interference creates a critical intelligence gap. While a tank can engage targets at 3 to 4 kilometers, the crew needs to identify threats at 5 or 6 kilometers to remain protected. They require aerial reconnaissance that can function without a persistent connection to the global satellite network. Navigating this environment requires a transition away from signal-dependent navigation and toward internal, onboard logic. Welcome to autonomous warfare. To see how these machines construct their own sense of location in the dark, hit that subscribe button. This is the Teledyne FLIR Black Recon. It is a tactical micro-UAV designed to weigh under 450 grams, hit top speeds of 25 meters per second, and maintain a 60-minute flight time. The system operates from a hardened launch box mounted to an armored vehicle, cycling up to 3 drones through continuous missions. As one drone returns to dock and recharge using an autonomous cradle arm, another launches to take its place, providing the crew with 24/7 overwatch. When the drone encounters GPS jamming, it immediately defaults to its inertial navigation system. It uses onboard MEMS-based sensors to measure acceleration and rotation, allowing it to dead reckon its flight path for 60 seconds without any external data inputs. Because inertial sensors accumulate drift over time, the drone uses its onboard cameras to identify unique physical landmarks in the environment. By matching these visual features against a preloaded geo-referenced map, the system calculates the discrepancy and resets its exact coordinates. This map-assisted correction results in a 94% reduction in absolute trajectory error compared to pure inertial navigation. It allows the drone to maintain its flight path even when its primary satellite sensors are completely neutralized. In environments where maps aren't available, the drone relies on visual odometry. Convolutional neural networks analyze the live camera feed to track how specific pixels shift across consecutive frames. By calculating this optical flow, the AI can estimate the drone's 3D movement and momentum with high precision. We see this technical split in the commercial sector as well. While DJI's Matrice 350 is the standard for large area mapping, the Skydio X10 utilizes a 6-camera array to support autonomous flight through complex, close proximity obstacles where GPS is often obstructed. However, optical cameras are limited by low light, smoke, and dust. To counter this, tactical drones integrate Millimetre-Wave radar modules weighing under 150 grams. These radars emit high-frequency pulses to perceive surface structures and relative motion, even in total darkness or heavy electromagnetic clutter. By fusing these radar returns with inertial data and visual neural networks, the drone maintains a stable odometry solution. This multi-layered approach ensures the machine retains spatial awareness when human eyes and standard optical sensors are rendered ineffective. Tracking movement locally allows a drone to avoid obstacles, but it doesn't provide global context. To execute a mission, the drone must still verify its absolute global coordinates without a satellite link. This is the Geographic Information Guided Contrastive Learning Framework, or G2CL. It utilizes a Siamese network with 2 branches to simultaneously process the drone's live camera feed and stored satellite imagery of the same geographic area. The system employs an InfoCE loss function to calculate the haversine distance between these 2 perspectives. By dynamically adjusting the distance between image samples in the feature space, the model learns to align the drone's angled view with the vertical satellite data. By referencing datasets like dense UAV, the system learns to extract fine-grained spatial features. This allows the drone to identify its location by recognizing how buildings and roads are distributed, even when the viewing angles between the drone and the satellite images don't match. The G2CL framework effectively serves as an onboard replacement for GPS. It allows a drone to independently verify its absolute global position through raw visual matching, providing a sovereign navigation capability that cannot be jammed. The final electromagnetic threat is spoofing, the use of counterfeit satellite signals to inject false coordinates into a drone's navigation filter. If successful, an enemy can misdirect a drone toward a hostile zone or cause a premature mission abort. To counter this, the onboard AI uses the drone's physical momentum as a truth reference. It compares incoming GPS data against its own inertial and visual estimates. If a satellite update reports a jump in position or velocity that is physically impossible, the system classifies the signal as non-credible and rejects it. The drone also protects its command link using frequency-hopping spread spectrum and beamforming. By rapidly switching frequencies and focusing its energy into a narrow, directed lobe, the system increases its resistance to jamming while making its radio signature significantly harder for an enemy to triangulate. If a single unit in a swarm is affected by an attack, the distributed network provides a final layer of defense. The drones continuously exchange state information, and swarm consensus algorithms identify any unit whose reported position diverges from the predicted geometry of the formation. By integrating these internal integrity checks and frequency agility and swarm-level consensus, the system identifies and isolates corrupted data before it can degrade the overall mission logic. Small drones have evolved into systems capable of complex multi-sensor fusion. By performing every calculation for flight stability and navigation entirely on the airframe, they can operate independently of GPS and remote pilot links. The applications for this self-reliant logic extend beyond the battlefield. By 2027, the same Black Recon systems tested in the Arctic environments of Norway will serve as autonomous first responders for border security, critical infrastructure monitoring, and maritime patrol. Thanks for watching. If you want to keep exploring the systems reshaping our world, make sure to like and subscribe to Autonomous Warfare.